Welcome back. Let's get started with motifs and network perturbations. These are a couple of very interesting concepts in the context of networks. We already looked at community detection yesterday and modularity and so on. I'll start with a simple example, just recapping one of the community detection problems that we looked at yesterday, Zacharys Karate Club. So let's look at a quick aside of Zacharys Karate Club. This was a study conducted in 1977 by Wayne Zachary. He was studying a social network capturing friendships among 34 students at a university karate club. And as luck would have it, there was an infight within the karate club and the group split into two. And many community detection algorithms are able to accurately predict the two factions or communities within this karate club as they split. And this has become like a very standard data set for studying community detection algorithms and so on. There are like t-shirts which says that if your algorithm doesn't work on the karate club data set, you go home, things like that. There is this very funny karate club where which is a sort of a trophy that is passed on for the first reference to a karate club data set in any networks conference and so on. So there are these kinds of funny things that you can read about, and this is how the network looks like. So on the left hand you see the complete network, and on the right hand you see as you apply the Girvan-Newman algorithm, how does the network change, right? So you see that there are 5 colors, 4 colors, 3 colors, and ultimately 2 colors, which captures how the karate club split very nicely. So now let's look at motifs. What are motifs in networks? So what are motifs? It's not a word that we commonly use in the English language, but even in the English language it means that some sort of a symbol or a logo or like a pattern, and that's literally what it means in the context of networks as well. What is the pattern of connection between nodes? And obviously we are looking for not just any pattern, but patterns that repeat often enough. So let's see how to get there. So what are motifs? Not all subgraphs in the network occur with the same frequency. So there are some subgraphs which are very much overrepresented in the network, and motifs are these overrepresented subgraphs, and one could call them statistically significantly overrepresented subgraphs in the network. Overrepresented with respect to what? This becomes a very interesting question, and I would like to take the next few minutes to make you think about this notion of what is an expected value versus what you see in the network, and how that gives rise to statistical significance. So let us completely change gears and talk about a very distant topic. And let us talk about like a clinical trial. Suppose you have a drug that is supposed to cure COVID, okay, and how would you test for the efficacy of the drug? So let's talk about some basic statistical testing. I'll not go into all details of statistical testing. I'm sure you've done it in previous courses and so on. But the problem here is that you want to show that a particular drug, a particular concoction is more efficacious against COVID compared to not having a drug at all, compared to just leaving the disease untreated. So how do you go about doing this? So you will immediately say that you need to establish a control group and a test group. You have a control group with n number of participants, and you have a test group with the same n number of participants typically. And then you will say that I want to make these groups as homogeneous or as equal as possible. I have to do an apple comparison at the end of the day. So these two groups must be as equal as possible, which means that I should have the same number of males, same number of females, same people in the age group of 40 to 60, same people in the age group of 60 to 80, whatever. I want to keep the two groups as close as possible. Why? Why do we do this? Because otherwise you cannot make a strong statistical conclusion. Suppose the drug worked for one group and the other group is the control group for which we didn't give the drug, and you may not be able to still conclude, because you can say that, oh well, it worked on this group because these people are all young, and that group had relatively older people, that's why it didn't work, or something like that. So there is always this notion of you have to make an apple comparison, which means that you need to bring the two groups as close as possible. That is challenge number one. And then what do you feed those people? You typically say that you feed the other group with a placebo. And what is placebo? A placebo is everything that is there in the drug minus the active ingredient. So suppose we were talking about paracetamol, like, so or we were talking about like something like Crocin or Dolo 650. So we have these drugs which are your generic paracetamol drugs you get in the market, but if you want to compare, the main ingredient is paracetamol, but there are typically other things that go into the drug formulation along with paracetamol. There is some excipient, there is something that holds the tablet together. In paracetamol tablets are typically white, but you have other tablets which have a color, right? So suppose you don't include the color in the control group, you can say, you can only statistically conclude that either the color or paracetamol is causing an improved reaction in the test group compared to the control group. So if you have to say that it is the COVID drug or it is paracetamol that is causing the exact effect that you want to demonstrate, you need to be able to show that, you need to be able to build these groups in such a way and give them appropriate concoctions in such a way that the only difference between the control group and the test group is the drug of interest, the active pharmaceutical ingredient, API as they call it, of interest. It could be paracetamol, it could be whatever COVID drug you are talking about or whatever. So the point I am trying to emphasize is that you need to make these two groups as identical as possible, first thing, because you don't want to say that you want to be able to attribute everything to the only difference between the two groups. If age is different in the two groups, you can attribute any response to the difference in age. If gender distribution is different between the two groups, you may have to also consider attributing any difference between the responses of the two groups to gender. So if you want to attribute all the differences to the drug itself, then that should be the only difference between the two groups. Now, why did I give you this whole backstory? So now I want to compute motifs in a network, right? So, and I have to say that there are some motifs that are statistically significantly overrepresented. With respect to what? What can I compare this network with? So this brings us to a very interesting question. So I have a network A, and I have to compare it with a network B, right? In fact, I have a network A and I am going to compare it with a population of networks or an ensemble. Okay, let us not say B, let us just say an ensemble of networks. We have already done this in the context of looking at small world networks and so on. How do you keep the networks as close to each other as possible? What are the properties that you want to retain? If you remember small world networks, the properties we retained were n, which is the number of nodes, and m, which is the number of edges. The catch here is that, so when you do this, someone can always say that, oh, any node, any network with the degree distribution that A has will have these kinds of motifs. It's not really because of any other biological process, right? So the stronger you make the control versus test group, right, the stronger you, the closer you bring them, right, which gives you more statistical power in whatever you want to say. So now let us say we had the degree distribution also same or whatever. So, we had absolutely close, the ensemble really captures the properties of the real network as close as possible, but of course, it is randomized in some way, right. So, which is why you get an ensemble of networks. This is also very closely connected to the concept of bootstrapping. You can go read about it, but basically you have a full ensemble of networks on the one hand, and you have your real network on the other hand, and now you show that there are properties of the real network which are very different from the ensemble. When you do this, you can now say with confidence that all these are attributable, all these differences are attributable to the processes that caused or that generated the real network. And typically we want to say that, oh, there is a biological significance for these motifs, there is a biological significance for this kind of connectivity, there is a biological significance for whatever property, could be a centrality measure or whatever, in the real network, which is not observed in the random networks. The random networks are very close to the real networks in as many attributes as possible in terms of size, in terms of connectivity and so on, yet they do not have those signatures, which means that these signatures have arisen owing to certain biological processes or certain, if you are talking about some real world networks, due to some human interventions, human design processes or whatever. So, this is the claim that we want to make. So, what is it that we are doing here? This is essentially hypothesis testing. Your null hypothesis is that your network has there is nothing special about your real network. Your alternate hypothesis is that my real network has certain very interesting signatures, whatever they be. It could be motifs of a particular size, motifs of a particular nature, it could be higher connectivity, whatever. It could be, or this is exactly running a parallel to the drug case. This is saying your null hypothesis that the drug is no different from the placebo in terms of its effect in curing the disease, COVID or headache or whatever. And your alternate hypothesis, which you have to be able to, the null hypothesis you want to reject on the strength of data, right. So, the data has to be collected by establishing the strong control group. So, I hope this is now clear. So, let us come back here. So, what are motifs? Motifs are statistically significantly overrepresented subgraphs in a network. But how do you now say that something is overrepresented? Which means that you need a sort of background expectation. What is your background expectation? For example, could you say that 7 feet fast bowlers are the norm in cricket, right? So how would you say this, right? And I mean, we occasionally find a really tall fast bowler, but you do not have 7 feet fast bowlers that commonly, right. So, you can, the moment you see a 7 feet fast bowler, you will always say that, oh, this is a rare person, right. So, he is like really tall, so he is going to extract a different kind of bounce of the pitch and things like that. But a 5'7" fast bowler is not a big surprise, right, or a 5 foot, maybe 5'7" is probably a little surprising because it's slightly on the lower end, but a 5'10" fast bowler is really not going to be a surprise. Most fast bowlers would be around that region, because you already have an expectation, you have established an expectation, you know that fast bowlers are typically of the height 5'10" or something, with a standard deviation of say 3 inches or something like that. So, when it is way more than that, when you have a 6'5" fast bowler or a 5'4" fast bowler, they are very different, right, they are on either end of the spectrum. This is because you have like a clear expectation, you know the distribution from which this is drawn. So, it is very easy for you to compute like a Z score or something to say how unlikely or how far from the mean is this particular observation. How do you do that for motifs? Use the ensemble. You have the ensemble that we talked about, you have an ensemble of networks, you now compare with that ensemble and say that, oh, I find certain motifs, right. So, certain subgraphs So, it could be a graph like, let us say this is a motif, right. There are other kinds of motifs, and directed motifs are more interesting and so on, but just let us just take this for argument's sake. So, this is a subgraph where you have 4 nodes which are like sort of connected in a particular fashion, that is not all nodes are connected to each other, there is one pair of nodes that are disconnected, otherwise all other edges exist. Okay. So, this is a motif. So, let us say this occurs 50 times in your real network, it could be like a yeast protein interaction network for all we care. Now, you compare this with the ensemble, and in the ensemble you plot a distribution of how often this motif occurs. Let us say the distribution looks like this, and let us say this number is 20 and this number is say 5 or something, and 50 is not even in my picture. So, 50 is so far out. So, 50 is a very unlikely observation if your real network were to be drawn from this distribution, which means that you can reject your null hypothesis that the real network is boring or the real network is basically from the same distribution as your ensemble. Your real network has some underlying processes that have made it very different. This would be our conclusion. You can always think of computing a p-value and all of that. So, I hope you know what a p-value is, but there is one nice way to think about p-value, which is it is a measure of lack of surprise. So, when you have a very rare observation, it is meaning a very surprising observation, it corresponds to a very low p-value. When you have like a very boring observation, very expected observation like a 5'10" fast bowler, it is going to have a very high p-value because it is close to the mean of the distribution or whatever. So, this is the way to start thinking about it. Now, the question is, how do you construct a good ensemble? And what do we mean by a good ensemble? Go back to the discussion we had a few minutes ago. You need to have the ensemble to be as close as possible to the real network, which means it should share as many properties as possible with the real network. So, we said it should have the same number of nodes, same number of edges, and why not the degree distribution as well. So, you have real networks, you have a real network on the one hand, and you have an ensemble of real like random networks which satisfy several properties. So, if you were to just use Erdős-Renyi, you would use simply GNM, right. You will generate networks of the same size, same number of same size meaning same number of nodes, edges meaning same density, but that is not sufficient, or I am arguing that that is not necessarily sufficient, because one can always say that in any power law network you will find this kind of motif. So, it is not really because of any biological process. So, this kind of argument one can put, but then if you actually build power law networks very similar degree distribution to the real network and show that this motif is present 50 times in the real network and has this kind of a distribution in the ensemble, you can now say that well this kind of motif has arisen because of a biological process, because there is no way it seems to occur in random networks of similar size, density and even degree distribution. So, this is how you want to make this statistical argument and identify motifs in networks. So, let us go ahead. So, how do we make these networks that are, how do we make this ensemble that really mirrors the real network as closely as possible? So, this is a very interesting question, and note that the number of distinct subgraphs grows exponentially with an increasing number of nodes. So, it is very challenging to even count these motifs and so on. So, we will there are other strategies like sampling and so on, but this can be quite a challenge.